This first question requires no calculation. The first thing you should do with any acid and base problem is identify whether the acid and the base are strong or weak. Both of these are strong. Okay, therefore the pH at the equivalence point is totally neutral. pH equals 7. You can see that when you write out the net ionic equation for the acid-base reaction. The molecular equation shows you, as all acid and base reactions, you get water and salt. But then when you write the net ionic, and if you remember those rules, you separate strong acids and bases, and you also separate soluble salts. So I'm going to separate everything I can. You can't separate water because it's a covalent compound. It doesn't have any ions to separate. Sodium chloride is a soluble salt, so it gets separated. Cross out everything that is the same on both sides, the spectator ions. And your net ionic equation for the reaction of a strong acid with a strong base is simply the production of water. That's why at the equivalence point, pH for a strong acid and a strong base together, pH will always be 7, neutral. One of the first things you want to do with any titration is make a note of where you are in the titration. This one says you're at the end point. Okay, that's about the same as the equivalence point. End point simply means when the indicator changes color, which hopefully is very close to, if not identical, to the equivalence point. So we're at the end of a titration. At the end of a titration, you can use this handy-dandy equation. Some of you forgot what little a and little b are. You need to know those, guys. So little a is the number of acidic hydrogen atoms in one molecule. It has nothing to do with the large coefficients when you balance equation. It has everything to do with how many are in one molecule. So A is 1. The molarity of the acid is, oh, that's what we're trying to solve for. Okay. The volume of acid, 25 mils. Again, it doesn't matter what units you use for volume as long as you use the same units on both sides. Now, little b is the number of hydroxides in one base molecule. Well, the one base molecule is calcium hydroxide. There are 2 hydroxides in one molecule of calcium hydroxide. So little b is 2. Molarity of calcium hydroxide is 0.0126. And 17.8 milliliters of sodium hydroxide was used. Then you simply solve for the molarity of the acid. And plugging all that into the calculator, you get the molarity of the acid is 0.0179 molar. So A was the correct answer. I think just reading this problem might get confusing for some of you. So it might help if you make little notes about things that you notice. First of all, we're at the equivalence point. We're at the end, okay? And here's the strong acid. Okay. Hopefully you know that this methylamine is a weak base. I've said enough times that anytime you have a compound with a neutral nitrogen in it, no plus charge on it, it is a weak base. All right, so basically what we're doing is titrating a weak base. So the first thing to do, even if you don't know what you're doing, write either an equilibrium out or a reaction out. In this case, there's no equilibrium. We have a strong acid, so it's a titration reaction. So HCl plus this weak base. I noticed a lot of you had trouble writing a reaction. And I want you to remember that acids, remember, donate a hydrogen ion, okay? And so literally this is all you need to do for an acid-base reaction is move a hydrogen atom from the acid to the base, okay? So when we do that, our originally weak base adds another hydrogen, takes on a plus charge, and it is the conjugate acid of the original weak base. What's left over after this HCl donates the hydrogen? We have chloride anion, okay? So remember, we're at the equivalence point, which means all of the reactants have been obliterated, reacted with each other. They're gone. And the only active ingredient you have at the equivalence point is this conjugate acid of the weak base, right? So you need to figure out how much of this conjugate acid you have, and then it's simply a weak acid ice table, okay? This is a weak acid. Forget the titration equivalence point, if you were just given this substance, told that it was a weak acid, and to calculate the pH, what would you do? You would write this weak acid in water. All these reactions take place in water. They're all aqueous reactions, by the way. If you were to put it in water, the equilibrium would be typical for a weak acid. Okay? In other words, now this is the acid, so it would give one of its acidic hydrogens to water, which is serving as the base in this equilibrium. And doing that regenerates the original weak base and hydronium ion. Okay? This is an equilibrium, and so you would set up an ice table, which I'm going to do on the next page. All right, so if you have gotten this far, be proud of yourself. It's almost halfway. And now you simply have ice table for a weak acid, except you've got to do a little bit of extra work to figure out your initial concentration of this weak acid. All right, so we know we're going to put these 0 just like we always do, plus x, minus x, and now we have to find this original concentration of the weak acid. Now, I'm going to write how you do that. Find the original moles of what you started with, which was CH3NH2, the weak base. Okay, when you find the moles of that, that equals the moles of the conjugate acid that we're worried about, because they exist in a 1-to-1 ratio. For every 1 mole of the original weak base that reacts, we make 1 mole of its conjugate acid. Okay, so the first thing you do is go back to the problem and calculate how many moles you have of the original weak base. Go back and read the problem. This methylamine said we used 20 milliliters. I just converted it to liters. And the molarity of it is 0.2502 moles per liter. Okay, multiply those together to get moles. And we find that we started with 0.005004 moles of CH3NH2. Okay, and the mole ratio of those two is 1 to 1. So for every 1 mole of the weak base we react, we form 1 mole of its conjugate acid. So we now know that the number of moles of the conjugate acid that we have at the equivalence point is this, okay? In order to fill out our ice table that we made, we need molarity. How do you find molarity? Well, now we have moles, but our volume has changed. Remember during a titration that you're constantly adding titrant, you're constantly adding volume. So the volume here is the total volume of everything you added together. And so that was, let's see, we had 20 milliliters of the methylamine. And then how many milliliters did we add of HCl to reach the equivalence point? If you go back to the problem and read it, it doesn't tell us. Well, any information at all you need to find about the equivalence point, and if you haven't realized this already, you need to write it down and highlight it. Anything to do with the equivalence point, you can go ahead and use our handy dandy equation. Okay, and we will use that to find the volume of the acid we added to reach the equivalence point. All right, so HCl was our acid, and so little a is 1. HCl only has 1 hydrogen. The molarity of the acid is 0.100 molar, and we are trying to solve for the volume of acid needed to reach the equivalence point. B is 1. Molarity of the base is 0.2502. I hope I'm remembering that correctly. And the volume of base used was 20 milliliters. So rearranging and solving for the volume of acid needed. Let's see, so the volume of acid used is 50 milliliters. Okay, so now that's to reach the equivalence point. So now we go back and to our total volume. Let's see, so the concentration of the conjugate acid that was formed at the equivalence point is 0.005 moles, which we calculated on the last page. And we now know that the total volume is 20 milliliters of the weak base plus the 50 milliliters of the acid titrant that we just calculated. And so, of course, now at this point, to get molarity, we do need to convert the milliliters to liters. Okay. So the concentration of conjugate acid is 0.0714 molar. All right, so now we can go back to our ice table. This is the original concentration of conjugate acid. So back to our ice table. Remember, all we're dealing with at this point is equilibrium of a weak acid. So we set up our ice table. We just calculated on the last slide that the initial concentration is 0.0714 molar. No surprises here. And since this is an acid, we need Ka. The original problem gave us Kb. So at the equivalence point, you always need to convert the equilibrium constant they gave you to the opposite. And it was 4.4 times 10 to the minus 4. And so calculating that gives us a Ka of, let's see, 2.27 times 10 to the minus 11. We can certainly neglect x with that small of a Ka. And that Ka then equals x squared over 0.0714. And x squared equals, let's see, 1.62 times 10 to the minus 12. Take the square root of both sides. And x, which is the hydronium ion concentration, equals, let's see, 1.27 times 10 to the minus 6. Okay, that's hydronium ion concentration. I don't want to open up another page, so we need to take the minus log of that to get the pH. And that gives us that the pH at the equivalence point is 5.89. Okay, and remember we started off titrating a weak base, that's methylamine, and so we expect pH at the equivalence point of less than 7, and so that fits with our expectations. All right, boy, after that last one, does you in. Okay, so here we're dealing with a titration. We do have a weak acid. It doesn't even matter what its structure is. You can just call it HA, whatever. And we have to determine whether we're at a special point in the titration. The special points are before it ever begins, the halfway point, and at the equivalence point. So let's figure out how many moles of each we have. That way we can kind of figure out where we're at. So 25 mils times 0.3 is, we have 7.5 millimoles of the weak acid. And let's see how many millimoles of sodium hydroxide we have. Excuse me. So 25 mils of sodium hydroxide times 0.1 mole per liter. So we have added 2.5 millimoles of OH. Okay, I usually just knock sodium off there and do net ionic. So I'm going to go ahead and write the reaction that's going on, and we're not at the halfway point. Halfway point would be half of 7.5, so we're before the halfway point, not at the equivalence point. So this is just a typical titration of a weak acid, where the first step is always completing the mole table to see how much of each of them have reacted. And the second step is the Henderson-Hasselbalch equation. Thanks to Macy, the HeHa equation. And so here's the reaction. We have some weak acid. I'm just going to get rid of the sodium spectator ion. These acid-base titrations are not equilibria, by the way. As long as there's one strong component, it does go to completion. So we end up with water and then the conjugate base of the weak acid. All right, so now we can set up our mole table. I can't ever remember what I used for initials, whatever you want over here, before and after, and then change. So, and this is the mole table. So the original moles of the acid is 7.5 millimoles, which are the moles added of the base are 2.5. Remember now, however much of the titrant, in this case the base, you add gets subtracted. It all reacts. So you have 5 millimoles of the weak acid left. Of course, all the OH is gone at this point. And we forget water, it's a liquid. And you have created 2.5 millimoles of its conjugate base. All right, that's step one. Step two is to use the Hee-Haw equation and plug in. Remember, it's base over acid, so 2.5 over 5. So we'll go ahead and plug in the rest of the information to the Henderson-Hasselbalch equation. Alrighty, so this is all the information plugged in. Here's the value for Ka. So we now have, let's see, the minus log of the Ka gives us 3.80. And then we need to do the log of 0.5. And that is, let's see, minus 0.301. And that gives us a pH of 3.80 minus 0.301. And that gives us 3.5. Oopsie. For the pH of this problem. Okie doke, I had to wait for my dog to stop barking. So here's the Henderson-Hasselbalch equation. I plugged in everything the problem gave us, the pH. This will give us the pKa minus log of the given Ka. And then we are trying to solve for this ratio. So let's see, let's simplify what we can. The minus log of 1 times 10 to the minus 5 is 5. And I'll just do it step by step. All right, so now we can definitely subtract 5 from both sides of the equation. And so that gives us 0.5 equals log of our ratio. And to get rid of the logs, it's 10 raised to the power. Okay, so the 10 and the log negate each other. So what you end up with is 10 to the 0.5 equals the ratio that we want. Okay. So what is 10 raised to the 0.5? And my calculator says that that ratio is 3.16. Oh my, sorry about that. Okay, so the last two problems were Ksp, and I think you guys are really rusty on those. So we are going to practice Ksp on Wednesday, but let me go through the basic steps. If you have a Ksp problem, or if it says Ksp, or you identify that there is a slightly soluble salt, the first thing I want you to do is to write the equilibrium out and set up an ice table, okay? It's very dangerous to try to not do an ice table for Ksp. I didn't see anybody in either class do that successfully if they skipped the ice table. All right, so Ksp problems, the original salt is just about insoluble, and so it does not affect the equilibrium. And original concentrations for the solvated ions are 0 unless it's a common ion problem. And now is where you need to be very careful. Plus x, pay attention to the coefficients. Remember that subscripts become coefficients when you solvate a salt. So this is plus 2x. Now, write out the generic Ksp without any x's. That's another very common place to make a mistake. Is you have to remind yourself that this fluoride concentration is squared. Now and only now, plug in your values. For solubility. Now, some of you fell into the trap and you didn't realize what this number was. Solubility, remember, is a molarity. It is not Ksp. Okay, solubility is not Ksp. So don't plug it in for Ksp. Solubility is concentration or X. Okay, so basically what they're telling us here is that X is 8.4 times 10 to the minus 3. So if we plug X into these equations, we get 4x cubed. And you know what x is. All right, there's a commercial with dogs. I'm going to go ahead and calculate what that is. Alrighty, so then we get, when we plug all that in, that Ksp equals 2.37 times 10 to the minus 6. Now, some of you were savvy enough doing this that you realized right away that the number they gave you was x. And if that's the case, you don't need to even write the x's in here. If you know what x is, you can just write it in instead of using x. Okay, so if you did it that way, it's perfectly fine. Last problem. All right, so first of all, hopefully you can identify it's a Ksp problem. So before you even concern yourself with that, the instant you see it's a Ksp problem, you should write out the equilibrium of the insoluble salt in water. Okay, and get your ice table set up. Okay, I'm just going to hold off for a minute. In this case, they gave you Ksp. Okay, and so there we go. Now when you kind of get the skeleton set up, you can go and look at what is this. Okay, well, HCl is a strong acid, which means how does a strong acid exist in water? All of these reactions, this whole chapter, if you look at the title of the chapter, is aqueous reactions, so they're all in water. And so a strong acid will immediately dissociate completely. And so look at this. Turns out that HCl is a source of the chloride ion, which is a common ion. So the beginning concentration of chloride ion is not 0. It is 0.15 molar. Okay, this is very similar if you're in Chem 2 lab to the Ksp lab when I think calcium chloride was the source of the common ion. But it's very similar to that problem. All right, then the change you're going to get is you're going to get some buildup of X from the lead chloride dissolving. It would be 2x for the chloride, okay? And so you add everything together. So your equilibrium concentration of lead ion is X. Your equilibrium concentration of chloride ion is 0.15 plus 2x. Now, you always want to see if you can neglect the X that's added to some other number. So let's take a look at the K value, the equilibrium value, and yes, it's quite small, 10 to the minus 5. So I would say we're safe to neglect that X. And I want to point out at this point that I just had to back up because I did not write out my generic Ksp expression like I always tell you to do. That is without any X's in it. And because I did that, forgot to square the chloride. So I had to erase, back up, start over. So please do this all the time. So now plug in the X's. Okay, so we have X for the concentration of lead ion and, 0.15 squared for the chloride concentration. And 0.15 squared equals, well, that's not right. 0.0225x. Okay, and then solving for x is 1.6 times 10 to the minus 5 divided by 0.0225. And x, remember, x is a molarity term, a solubility term. Okay, so that will be our answer. It's asking for solubility. So let's see, 1.6 times 10 to the minus 5 divided by 0.0225. And so x is 7.1 times 10 to the minus 4 molar. That is the solubility of lead chloride in water. That is it